a lattice.
All right. Can I borrow somebody's pointer? Sorry, did you just put it away? Yeah, that's my fault.
I've got another one here too.
Thanks. Do you want me to just use this one? Okay. Sorry about that. Thank you. Thanks, Stefan. Okay. All right. Hi, everyone. Thanks, everyone, for being here. Thanks to Steve and the organizers for putting together this nice workshop within this bigger superconductivity conference. And that allows me to be here, even though I won't talk about superconductivity. So I am Ankit Disa. I'm now an assistant professor at the School of Applied and Engineering Physics at Cornell. The work I'll be talking about is work that was carried out when I was a postdoc in the Max Planck Institute in Hamburg. And what I'll be telling you about is essentially what's shown here, how we can use light to essentially control the order parameter of some particular electronic or magnetic phase. And I'll try to tell you that we can do this actually in a pretty rational way now by taking advantage of the coupling between light and the crystal structure. So I want to first start by acknowledging all the people that were involved in this. As I said, this was carried out in Hamburg in the group of Andrea Cavalieri. I especially want to highlight Michael Fechner for a lot of theory support, as well as John Curtis for theory support, and the excellent samples that we got from the Oxford and the Stuttgart groups. Okay, so as I said, I won't, unfortunately, be talking at all about superconductivity, but I have thrown in a few nods to superconductivity here and there, just to kind of fit into the conference. So for example, here I'm showing you what is maybe now a somewhat outdated phase diagram of the generic phase diagram of the cuprates. You have at low doping, magnetic order, intermediate doping, you have a superconducting order at low temperatures. At high doping and high temperatures, you have metal phases, strange metallic phases. You have other phases that pop up in and out of the phase diagram. And the point of me showing you this is just to show you that what we have in this kind of system is something that has many, many different electronic and magnetic phases that can be tuned via some tuning parameters. So the system is quite complex and has a number of different possible ground states. And this is something obviously that's not specific to cuprates. You have this in many other strongly correlated systems like manganites. You have different magnetic and charge and orbital orders. But it's not even that specific to, let's say, strongly correlated systems. If you just take a look at a simple ferroelectric like PZT, you end up with a lot of different structural phases that can be either ferroelectric or not ferroelectric, or there's some of the anti-ferroelectric. And so the point is that there are many different systems with different types of order parameters that have this tunability, and this ability to go between different types of phases via some tuning parameter. Okay, and if I may sort of summarize what I think some of the goals of many of the people in this particular conference are, if we look at the phase diagram on the left, I think it's twofold. One is to kind of understand what is this phase diagram, right? What are the different phases? What is the underlying physics of the phases that pop up here? But on the other hand, which is kind of the camp that I fall into, it's to understand how we can manipulate this phase diagram and obviously try to elevate TC and do this. And what I will talk about is how we can do that in different types of systems rather than superconductors and magnets and ferroelectrics. And the way that we can do that, I think a very direct way to do that is by coupling to the crystal structure, taking advantage of the fact that the lattice is strongly coupled to all the other electronic and magnetic degrees of freedom in the system. This is pretty obvious that this can be done in the case of many different systems. In the Hubbard model, if we change the lattice, we change the hopping, the bandwidth, and the effective interaction parameter. In magnets, if we move around the lattice, we're going to change the exchange interaction. We're going to change the local anisotropy. And so the crystal structure gives you this knob, right, to tune local electronic and magnetic states as well as their interactions. And so in equilibrium, we can take advantage of this by applying pressures and using that to tune the lattice and its interactions, and then we end up with phase diagrams like this, where as a function of pressure we get different phases, or we can change the temperature of some phase. But there are, of course, limitations to this, and what we'd kind of like to be able to do is to achieve this kind of control without having to apply extreme pressures. And so the dream is essentially to be able to go beyond this equilibrium phase diagram to control macroscopic order, to control order parameters, and induce new phases and functionalities that maybe can't even be accessed in equilibrium with pressure, for example. Okay, and so what I'll be telling you about is how we can do this using light, and instead of applying static pressures, we'll be shining light directly on the crystal resonantly with its vibrational modes. And we do this, and by doing this, we can drive large amplitude structural distortions that can be on the order of several percent of the interatomic bond distances. To do this, we need to resonantly excite optical phonons that typically have frequencies in the few terahertz to mid-IR frequency range. So we spent a lot of time in Hamburg developing new sources that can now span really this whole range with really, really intense electric fields, which allow you then to access these extreme atomic displacements. And the important point is that when you drive the system with such extreme displacements, the crystal lattice starts to act in a very nonlinear way. And you can take advantage of this nonlinearity to essentially engineer new types of crystal structures that may not otherwise be accessible. Okay, and so I will give you a couple of examples of how this works. And I will first start with a very simple example, which is an experiment that we carried out a couple of years ago now on this very simple antiferromagnetic system. And the idea here was to take this antiferromagnet, which is just a BCC lattice of cobalt ions, each one surrounded by fluorine. This is cobalt fluoride. It has a compensated antiferromagnetic order where on the corner, the magnetic moment is equal and opposite to the one in the center. It's very simple. And the question we had was, how can I control the order in this antiferromagnet? It's quite difficult because I can't just apply a magnetic field. How can I actually, let's say, switch the antiferromagnetic order or otherwise control magnetism in the system? And so one thing you can do in this particular case is to apply pressure. The unique property of cobalt fluoride is that if you apply a stress along the 110 direction, you will actually decompensate the two sublattices. One of the moments gets bigger and the other one gets smaller. And so you end up with a net magnetization, essentially a ferry magnet that comes out as a result of this that's proportional to the applied stress. Okay, so this is known as the piezomagnetic effect. It's a linear relationship, and it allows you to tune both the magnitude of kind of the induced magnetization as well as the direction. You can strain it in the other direction and you get the opposite magnetic moment. And this is really a powerful tool because it allows you to tune now magnetic order in an antiferromagnet. And it has, let's say, a number of potentially interesting applications for spintronics and memory, because antiferromagnetic spintronics is quite an interesting idea from the standpoint of using magnets for information processing. But the problem here is that this is really applying a pressure. So it's somewhat limited, for example, in the pressures that you can achieve before the crystal will break, and also the time scale by which you can induce this kind of change. So the question is, can you use light to say, circumvent these limitations and dynamically drive this distortion instead? Okay, and the way you can do that is essentially what we want to do is emulate what happens to the crystal when you apply a strain. This is a top view of the same crystal. And the main, let's say, result of this strain is that the in-plane cobalt-fluorine bond lengths become different. In equilibrium, the corner has an in-plane cobalt-fluorine bond length, which is D. The same one is there for the center. But when you strain the system, essentially one of them gets longer and the other gets shorter. This changes the local crystal fields on each site, so there's an orbital moment that is different now on this site and this site, and that's where you get this magnetization. So what we need to do is essentially emulate this same kind of anti-symmetric bond distortion in another way by using an optical phonon. And we can do that by looking at, let's say, all the different phonons that the system has. And you find that there's this B2G symmetry Raman phonon that whose eigenvector, eigendisplacement is shown here. And what you can see is that it has the same essential motif. One of the bond lengths gets longer when you distort this mode, and one of the bond lengths gets shorter. So you will get the same lattice distortions as uniaxial strain, which means that in principle you should be able to get a magnetization when you apply this distortion. But it's an optical phonon, so you're not going to be limited by the same constraints as this sort of volume distorting strain. Right? The caveat here is that you have to break the underlying symmetry of the lattice. You have to somehow excite this particular symmetry, Raman mode. And of course, at first glance, this seems like a little bit of a non-starter because when I think of the light-matter interaction, I can only couple to modes that have dipoles, infrared active modes. And so we should only be able to kind of wiggle around modes like this. Moreover, they should only be kind of wiggling with the electric field, and then they will die off. But as I said before, when we excite the system very, very strongly, a number of things can happen. And one of those things is that you start to pick up anharmonic terms of the crystal lattice, and one of them is a term that couples an infrared active mode, which you're directly driving, to a Raman mode. Okay? And so you can, by this mechanism, let's say indirectly excite Raman modes. And what's most important here is that this gives you a directional force. It only goes in one sign. So you actually get a distortion that is kind of quasi-static. Okay? And this is the effect that we use to try to achieve this Raman distortion that I talked about before. I'll just show you what the end result is. Basically, I'm just showing you a simulation of what happens when I actually excite a particular infrared active mode, which is coupled to this Raman mode. And what happens is that I excite this infrared active mode that's kind of this wobbling back and forth. But you can see that in addition, there's this kind of displacement of these bonds. Like that one only goes up, and on average, this one only goes down. And so you have, in addition to this vibration of this infrared active mode, you have this Raman displacement. Okay, so this is what's happening when I actually shine my light that's, let's say, resonant with some infrared active modes to very high amplitude. And I'll just flash you the results because I actually want to show you something else after this. When we actually tried to carry out this experiment, we used resonant terahertz pulses to drive this infrared active mode, and then we used magneto-optics to sense the resulting magnetization. And what we found is that you do indeed get a magnetization that you induce via this mechanism. It's switchable. You can go in one direction or another by changing the polarization of your pump pulses. And moreover, probably the most important or interesting thing is that we could achieve, at the end of the day, an induced magnetization that's about 0.2 Bohr magnetons per formula unit, which is about 100 times more than you could possibly achieve by stress. The crystal will break before you can achieve anything more than 100 times less than this. So this is something that kind of demonstrates that this approach of dynamically driving the crystal lattice really gives you something that you cannot necessarily achieve in equilibrium, and you can do this by optically driving phonons. Okay, so this is just one example. I'm sure you're all familiar with the fact that there are many, many other examples of using this so-called nonlinear phononics to manipulate different electronic and magnetic phases. You can manipulate magnetism. We showed that you can create a metastable ferroelectric state in this way. And of course, there are many examples of light-induced superconducting states. What I will be talking about now is how we can possibly extend what I just showed you to higher temperatures. This ability to manipulate antiferromagnetism at low temperatures was limited to below the nail temperature. I had to have this antiferromagnetic moment already. The question is, can we somehow extend this non-equilibrium behavior and induce magnetism at temperatures above equilibrium Tc, something akin to this high temperature light-induced superconductivity, but maybe in a more sort of controlled and simple example system. Okay, and so the system that we looked at to try to explore this question is the rare earth titanates, and I'll explain to you why we chose the system in the next couple of slides. It's a orthorhombically distorted perovskite. And microscopically, the most important thing is that you have a single d electron, which is this titanium D1, so it's a spin 1/2 system. And this electron lives in this titanium T2G orbital manifold, and it's slightly split by this orthorhombic structural distortion. But the distortion is not so big, so you do end up with a high degree of orbital degeneracy. And in this type of degenerate T2G system, one can kind of immediately see from simple Goodenough-Kanamori type superexchange arguments that the orbital configuration that you have for the different titanium sites in this unit cell is going to be intimately connected to the magnetic interactions and the magnetic ground state that you end up with. That is, whether or not the system will be ferromagnetic or antiferromagnetic. And this can be seen very simply. Let's imagine that you have, on this titanium site, for example, dxy, the orbital ground state is dxy. Then if I have on the next site the same orbital, just through superexchange arguments, I would imagine that there's an antiferromagnetic interaction. So I will have an antiferromagnetic ground state if all of them have the same orbital. But if we have different orbital on the next site, we'll have a ferromagnetic interaction. And so in a kind of perfectly degenerate system, you have frustration. You have the frustration between these two different interactions, and you have a very highly entangled and highly degenerate ground state, which leads to very strong fluctuations up to very high temperatures. This is, let's say, known. This was deemed an orbital liquid, in analogy with spin liquids, by Keimer and colleagues a long time ago. In reality, as I said, there's an orthorhombic distortion, so the degeneracy is split, and the system actually chooses one particular orbital and magnetic ground state. But you still have a system where there's a very, very strong coupling now between the crystal lattice, the orbital configuration, and the magnetism. And this shows up in a number of different ways. One is that the magnetic order is very tunable by changing the structure. So here I'm just showing you a phase diagram of the titanates where I'm changing the rare earth ion from yttrium to lanthanum. And that changes the amount of structural distortion that you end up with. And you can see that basically, as I change the structural distortion, in this case, if I make it less by going to lanthanum, I change the ground state from ferromagnetic to antiferromagnetic. So you have a very strong tunability of the magnetic order with the structure. And what I'll be talking about, I'll be focusing on yttrium titanate, which is on the ferromagnetic side here. It has this particular orbital ground state, which ends up giving you a Curie temperature around 27 Kelvin. And there are a number of interesting experimental facts about yttrium titanate, which show signatures of these fluctuations that I talked about up to high temperatures. So one is actually that Tc here is about half of what you would expect it to be from the magnetic exchange that's measured by neutron scattering. Another couple of observations that have been made are basically that at very low temperatures, so this is at 4 Kelvin, and also at very, very high magnetic fields, this is 2 Tesla, but it goes all the way out to 7 Tesla, you end up saturating the magnetic moment significantly below what sort of the ideal spin 1/2 value would be, about 20% less. And this cannot really be explained at all by canting or by spin orbit effects. It's something that is perhaps associated with the fluctuations that I talked about before. Moreover, in various thermodynamic measurements, you find that, for example, the specific heat and the magnetic contribution to the specific heat and magnetic contribution to lattice expansion extend out to temperatures that are up to 100 Kelvin or more. So that's about 5 times Tc. You also have a spin lattice coupling effect that, again, extends out to temperatures up to 100 Kelvin. Okay, and so you have some indication of short-range magnetic correlations, at least, up to about 5 times Tc. Okay. And so what you have is a system that has, let's say, a high-temperature kind of precursor state before you end up in the actual magnetically ordered state, which has this fluctuations of the orbital and magnetic moments. And so this really makes it a perfect system to try to understand whether or not we can, let's say, first optically control magnetic order through the lattice because we know of the strong coupling, and also to possibly stabilize this fluctuating precursor state at high temperatures. So that was the goal of an experiment that we carried out on yttrium titanate. And so the experiment is conceptually very simple. It's a pump probe experiment. We pump the system. We pump the lattice with some resonant terahertz pulse, and we'll probe it using a time-resolved MOC. And for what I'll be showing you in the future, the most important thing is that the MOC signal that you'll see is proportional to the induced change in magnetization by the pump. Okay. And then what we did is we used kind of a new terahertz source that we have in Hamburg that's able to span the range between around 4 to 20 terahertz. And we essentially pumped a number of different modes of the crystal, which have different lattice distortions associated with them, which should in principle give you different changes to the effective magnetic order. And we explored what happens to the magnetization when we pump these different modes. Okay. So what I'll show you here now is the time-resolved MOC trace as a function of time. Before I show you, the important thing is that a positive signal means that I've enhanced the magnetism. A negative signal here means I've weakened the magnetism. And this is what we see. Here's where the pump pulse comes. And in blue, yellow, and red are the results for pumping these 3 different modes at 4, 9, and 16 or 17 terahertz. Okay, and what you can see is that depending on the mode that I pump, I either can enhance or weaken magnetism, first of all, and the strength of that change in magnetism depends also on the specific mode that I pump. Okay, so this is already something kind of exciting because it means that we have really for the first time showed a phonon-selective manipulation of magnetism. It's not just dumping energy from the light that changes the magnetic order. It really depends on the structural distortion that I drive. So that's already a very exciting result. But now we can kind of explore in more detail what this non-equilibrium magnetic state is doing. Okay, and so what I'll focus on is this 9 terahertz state, which has the largest, 9 terahertz pump, which has the largest effect. And I'll show you first what happens below TC. Here's the equilibrium magnetization curve, as I showed you before, which doesn't saturate all the way up to 1. And when I pump the system, here I'm just showing you the raw traces. If I convert this into a magnetization, what you find is that in the non-equilibrium state here at kind of long times, you end up with a magnetization which saturates very close to that ideal spin 1/2 value, which is somewhat suggestive of the fact that whatever fluctuations are preventing order from, are preventing the system from gaining its maximum magnetic order are perhaps being suppressed by the pump. What's even more suggestive, I think, is that this this limit here, the spin 1/2 limit, is actually followed, is actually maintained even when you increase the fluence. And so even at our highest pump fluences, we still really saturate at that same value. So it seems to be some really hard limit to the system. Okay, now we can see what happens when I go above TC. Here again is equilibrium, M versus T, and in the non-equilibrium state, here is the magnetization as a function of temperature. And what we see is something that doesn't go away at all at TC, but extends all the way up to at least 80 Kelvin, which is 3 times TC. And if we look at what is that magnetic state, let's say at 60 Kelvin, we see something that really follows let's say the ferromagnetic stiffness that you find just below TC. So it seems like a real non-equilibrium ferromagnetic-like state. And interestingly, this temperature dependence follows a lot what you find in equilibrium from these thermodynamic measurements of short-range spin correlations. Okay, so we can also then see what happens when we pump different phonons as a function of temperature. And what we find is that, very similar to what we found below TC, you can either enhance or suppress magnetism depending on the pump, which corresponds here to an enhancement or a suppression of the effective TC of this non-equilibrium state. Okay, so now we can try to understand what's happening in the system. We have this really interesting non-equilibrium state. The question is, what is driving this? One possibility is that you have essentially a direct spin-phonon coupling effect, where essentially changing the lattice parameter is going to change a little bit the exchange, and so you'll end up with an exchange interaction which is modulated by the pump. Okay. So this is one possibility, but what we've done calculations, and we find that, first of all, the effect is way too small, and also it's typically of the wrong sign. So this cannot explain what we see. We can think about heating, but we can rule this out because we see sometimes an enhancement. We see it depends on the phonon, so it can't be related to heating. We can also rule out optical effects. We can rule out strain. And so a possible model that we can think about is something where what we're doing is actually coupling the lattice to the orbitals. Okay? And we can model this using some effective Kugelkamsky type Hamiltonian, where we take into account the contribution from the lattice, the contribution from the spins, and also this interaction between the spins and the orbitals. And without going into the details really at all, I mean, the picture is basically that depending on the lattice excitation that we pump, we modulate the orbitals in such a way that the effective change in magnetic order is either enhancing or suppressing magnetism, right? It's just a very qualitative picture, but one way you can kind of visualize what might be happening here is if you imagine the orbital ground state of yttrium titanate. We can parameterize this in terms of 2 orbital angles, which tell you something about which T2G orbital is the ground state. And we can then come up with a kind of a fictitious phase diagram which tells us, okay, depending on what orbital is the ground state, what would the magnetic ground state be, right? And so we come up with this kind of fictitious magnetic phase diagram that shows you that you can get an antiferromagnetic, you can get different types of antiferromagnetic order as well as ferromagnetic order. The equilibrium state sits right on this border between ferromagnetism and antiferromagnetism. And so if I zoom in here, you can see how close to how close between these two states it lies. This is, you can think of as in some sense, as the source of these fluctuations. And so the model that we have is that basically when you pump the system, the orbital is moving in such a direction as to either enhance or decrease the effect of these competing fluctuations. Okay, so essentially, phonon driving enhances or weakens ferromagnetism through the orbital state. And in the best case scenario, we can enhance the ferromagnetism, again, to create a non-equilibrium ferromagnetic state with a TC that's 3 times larger than in equilibrium. And okay, this is just to show you that there is a real calculation we did which kind of corroborates this idea. Okay, so that's all I wanted to talk about today. I told you a lot, but the main takeaway message is that we're really at a stage where we can drive the crystal structure with light in such a way to engineer specific types of order and really enhance create enhanced non-equilibrium behavior that otherwise cannot be realized. These are a couple of the papers that I talked about today. Here is another paper that shows a little bit more of a summary of the whole field. And you can think of now, I think, where we're at with this nonlinear phononics in the same kind of space as you can think of other equilibrium means to control the structure of materials. And so I think in the future, combining some of these elements will give you really huge possibilities to control non-equilibrium states of matter. So with that, I just want to end by advertising that I'm starting a new group, and I'm happy if any students or postdocs would be interested to work with me. Thank you.
Thank you very much. So there are already a couple of questions.
Thanks for a very clear talk. So the question I have is, once you pump the system and you enhance the magnetization as you showed, I would have expected now you are not going to be so close to the fluctuating regime, but your fluctuations continue to extend up to 3 times TC or 5 times TC. So I guess my question is, why are there fluctuations once you have gotten well into an antiferro or a ferro state? Because the fluctuations should be dominating when that single electron has to decide which of the 2 orbitals should I be in.
Understood.
But once it has clearly gotten into one of the states, what is the origin of these fluctuations?
Yeah, okay, understood. So let's say, I think I understand your question. If you have a perfectly cubic system, right, and there's no structural distortion, the orbitals on each side can be chosen, let's say, at random, right? So you have this degree of generality. There is a small structural distortion, this orthorhombic distortion, but essentially the answer is that the orbital gap is not so big, okay? And so relative to say, let's say, temperature or to the spin excitation scale, the orbital gap is on the same order. And so fluctuations of the spins and fluctuations of the orbitals are kind of still allowed in that regime, if that makes sense.
So with the phonon, are you modulating the gap between the orbitals as well?
Yeah, exactly. This was actually the calculation that I show here. It's not a huge effect, but it's enough to do damage. So this is just in some normalized units, but you can see that for the different phonons we pump, you're actually changing the orbital gap a little bit, yeah. There's a couple of things you do. You change the orbital gap, but you also change the ground state, potentially, of the orbitals. But this is just a model. I mean, there can be other things happening as well.
Can I say one thing?
You can.
Well, yeah.
The key thing there, go back to that figure there. The key thing is that you have this quadratic dependence on the coordinates.
Right.
You
I
have
didn't.
an average effect.
Yeah.
Right.
It's not, if it was linear, then you would just be going about the equilibrium gap.
Right. I didn't emphasize that. Yeah. No, I didn't emphasize that. That's a really good point. It's very important that it's quadratic so that it always goes down or always goes up. Right.
Yeah.
Yeah.
Makes sense.
But may I ask a question which is related? But once that you have a phenomenon which is transient, so actually your induced magnetization lasts very long time. So we had up to 150 picoseconds was still there.
Yeah.
So, but then what is really, how can you really distinguish, say, the fluctuating regime with the ordered regime? So in the sense that when you show us the phase diagram, you just have this induced additional signal that stays. So of course, if you compare with equilibrium TC, you would say I'm extending it above, but actually, so for example, the duration in time is different below TC or above TC?
Let's say the rise time changes a little bit depending on when you're above or below, but it's not so sensitive to it. But you're right. I mean, we don't have, let's say, a direct handle on the fluctuations. This is kind of an idea of what might be happening here. But let's say what you can think of is that the phonon drive, let's say, enhances the exchange in some particular way, right, through this effect. Now you've given it this force, and now it will now evolve according to its own dynamics, right? So that's why you end up with very long time scales, because now you have all this angular momentum. It has to go somewhere. That's kind of the bottleneck there. But yeah, in terms of the idea of whether or not it's fluctuating and this and that, I mean, we don't know. Yeah.
When you had the diagram of all the phonons, it looked like the 17 terahertz had a much weaker oscillator strength. So do you think, I guess, I mean, like the calculations seem to suggest that the 9 terahertz phonon sort of is a lot more important. But I guess, could some of the difference between the yellow and the blue be just the weaker oscillator strength, or you know, are you still able to saturate the magnetization if you use a higher fluence at 17 terahertz?
Yeah. You find that for essentially all of them, you end up with some saturation at high enough fields. But I mean, the oscillator strength is different here, but also the strength of the spin phonon coupling is different here, right? And so it depends. There's a lot of different parameters that it depends on. But these were all compared at the same fluence. You can also compare them at the same, let's say, absorption, like total absorption, and you'll see something similar. Yeah.
I have, I think, two related questions. The first is related to the reduction in the moment.
Yeah.
And you alluded to fluctuations, but I was curious to know. I mean, the sort of first thought is that there's an orbital moment there, and that would be, you know, that's where you would get the suppression from.
Right.
So that's not.
That's too small. People have measured it. It's too small. It's on the order of like 1% or so.
Okay. And then, I noticed here that you're measuring the Moch angle, and so at some level, that's it's not a direct measurement of magnetization. And I'm wondering if you've thought about ways in which the phonon could be modifying the wave functions in the material in such a way that enhances the Moch signal without actually changing the moment. Oh yeah,
like you through some various optical effects. I mean, we thought about this quite a bit. We did a lot of calibration. So one thing we have done is a calibration of the Moch angle versus magnetization, right? You can do this in equilibrium and plot the Moch angle. So you know at least, let's say, if there are no changes in the magneto-optic constant, we know that this is going to be related to magnetism in this particular way. We also, in some sense, know that the magneto-optic constant is not changing because, I don't have it here, but we measured both the Moch angle and the Moch ellipticity. And if you do that, you can, let's say you can write down that the change in the Moch angle in its complex form, and you can relate it then to, let's say, changes in the optical constant plus changes in the magnetization. And since you have both the ellipticity and the angle, you can kind of invert this equation. And so we found that there changes in the optical magneto-optic constant are quite small, and it's like 10 to the minus 2 or something like that. So I think that's not what's happening here.
More questions or comment? Yes. Andy?
Hey, thank you. Great talk. So just in terms of the long-lived nature of the magnetic state produced by photoexcitation, so there are two questions. The first is a simple, I hope, experimental one, which you probably said and I missed. which is there a fluence dependence? I mean, is it the case that at short fluence you get like a little blip of magnetization and then it decays back to 0, whereas at long fluence it lives for a long time? Or is there no obvious fluence dependence?
To the time scale,
Yeah,
there's no obvious fluence dependence to the time scale.
Right, okay. And question number 2 is just, on the experimental side, what else lives for a long time? I mean, if the hypothesis is you've changed an average structure or something, is there anything else measurable that lives for the same long time that the magnetization lives?
Well, the structure doesn't live, the change in the structure doesn't live that long. The structural change is on the order of the phonon lifetime, which is like 15 picoseconds or so. I think what's the time scale here is just an angular momentum bottleneck. I mean, you've changed the magnetization, and so now the system has to recover back to its equilibrium magnetization, and it has to do that by decaying, like angular momentum has to decay. And essentially, the issue is that the atomic spin orbit, which is the way that it's going to do this, is small in equilibrium. And so it's just kind of stuck there until it can have enough like sort of atomic spin orbit to get rid of magnetization, if that makes sense. That's what we think is going on. Yeah, I think it will be much faster. Yeah, absolutely.
Okay, so let's thank again the speaker, and this is the end of the session.